So, that is what is wave equation, and then we can define velocity, get expression for velocity. See, what we have done so far is we said this is the wave equation, c square is related to. So, we can actually relate. How do I find out velocity? I mean, I have to, what I have properties of the air, the medium, because it will be a function of the medium itself. So, it is a function of the medium, therefore, properties of the medium should dictate what should be the velocity. As you know, velocity of sound in air, and that too through a metal, is different, or any other material like civil engineering material such as concrete or soil, it will be different. So, it is a function of the medium itself. So, we can actually define this, relate this C to medium properties, and let us do that. So, if I take a small dx element of the medium between A and B, partial, since it is partial derivative, so small delta x element we have taken at x plus del x distance. Now, what is happening? It will be compressed or expanding, right? It will be compressed or expanding. So, as if it is stressed, if I take unit area along the other direction, unit area along the other direction, right. So, some area along this direction. So, it will be compressed and expanded. So, this compression means there is it's kind of stress. Compression means there is a kind of stress, right. So, the stress is nothing but the pressure. Stress is nothing but the pressure above the atmospheric, right. So, that is the stress, and stress must be proportional to the strain. And what is the strain? Delta x is the original dimension. If delta y is a particle displacement of this element, is a small element. So, particle displacement, that means it has come out closer or gone away. So, delta y 0, delta y, that is the displacement. So, strain will be delta y by delta x, strain will be delta y by delta x. So, direction of the wave is like this. So, it has moved in this manner, and the particle has displaced. So, particle was originally at y displacement, now it is y dy dx, that is what I can write. So, strain would be given by del y by del x, and therefore, P must be proportional to minus E dy by dx, because P is the stress and proportional to y minus sign, because compression I am taking as positive. Compression shortening is actually delta y is negative. Shortening means delta y is negative, and that is my pressure positive pressure. So, there is a negative sign E dy dx. For a small element having pressure difference, strain is equals to del y by del x, and I can write pressure as this, right. Pressure I can write like this. Now, my pressure is also available from elsewhere. So, rate of change of pressure I can find out del p del x from my wave equation. So, also pressure is nothing but mass into acceleration. Pressure is nothing but mass into acceleration into per unit area, mass into acceleration per unit area. So, if my area is A, the force is del P into A and rho del x into del A. So, therefore, like minus del P will be equals to rho del x A, and here is the A, this is the force, this is the mass, A is the area, I am taking unit area. So, this is equals to 1. So, that is why multiplied by 1, here also multiplied by acceleration, multiplied by acceleration. So, this is nothing but the mass for unit area, this is the pressure that I have applied. So, that must be equals to the particle acceleration. Therefore, del P del x I can write as minus rho del square y, d square y dt square, or del square y del t square, actually I should be writing, because partial derivatives they are. So, partial derivatives, in fact both are partial derivatives. So, this should be written in partial derivative terms, and partial derivative terms, right, and this should be, this should be this Please correct it, right? And followed by this del P del X is nothing but earlier P we have found out was E dy del Y, this also should be like that. And so earlier we have found out P was nothing but minus E dy dx because strain, this was a strain. So del P del X I can get an expression from here like this, and I can get an expression like this. And remember these two ratios of these two, one was what? Wave equation C square. These two are related through C square. Remember del square y del t square is related to del square y del x square through C square. So if I take a ratio, dp dx I have found out, and this two dp dx I have found out, and dp dx is also is also this, and these two are equal. So if I equate these two from this both consideration, so E del square y del x square must be equals to rho del square y del t square, right? And this two ratio of these two, now I can use C square. So in other words, I can get a relationship between C, E and rho. Rho is the medium property, E is also bulk modulus of the medium, right? Because I am talking of volume compression and all that. So therefore, this I can write. This is again why I have written, I think it should be like that. So this can be written like this, and this is correct now this time. So replace this from the earlier equation, the wave equation, which was this. So C square must be equals to rho by, C square must be equals to E by rho. C square must be equals to E by rho. It follows from this, C square must be equals to E by rho. So E is equals to rho C square, whatever it is, and C square, so C is equals to E by rho. So that's what it is. C square is equals to E by rho, right? So velocity is dependent upon elastic modulus, or it's a bulk modulus actually, and rho is a density of the medium. This comes from earlier that we have derived. This earlier we have derived, now we have done this, and therefore we can relate this, and this comes something like this. This comes something like this, right? So C is under root E by rho, and that's what we use elsewhere also. You want to find out the velocity of sound in, say, any medium, steel, E by rho. Air it is around 340 meter per second. In steel it will be 5.5 or 5.6 kilometer per second. So order of kilometer per second. Now all our purpose was to define something called acoustic impedance. Analogy to electrical impedance, and also thermal also we had something. Now in case of electrical, current is driven by the potential difference. Here the particle, alternating current, right? It is driven by potential difference. Here the particle displacement or velocity is driven by pressure difference. So we define impedance as potential by the flow, right? Potential by flow. So P u x, this should be, this is in complex form, because now periodic sine function, cosine function, so it can be expressed in periodic function, E I omega, etc., in that form. So it will be in complex form, and Z is defined x I t. So acoustic impedance is a ratio of pressure to particle velocity. Acoustic impedance is ratio of particle velocity. And P, you remember, it was something like this. I think I am del x of this, and P is something like this. P, remember, P was something like this. If I write it from the stress strain relationship, I get something like this. And velocity, I have got omega y0 sine omega t kx. These two are common. So therefore my acoustic impedance is given as, omega 0 is not there, these are not there. So E k over omega, and how do k is what? Omega by c, omega by c. So this is omega by c, So, and what was E? What was E related to C? Okay, let's write it. So, E is rho E by rho is equals to C square. So, E is nothing but rho C square. So, I write it as rho C square, and K is omega by C, and this side is also omega. So, this goes away and this remains. What is this? So, acoustic impedance of the medium is rho into wave velocity, rho into wave velocity, right. Acoustic impedance is simply rho C. So, it is rho C, simply it is rho C, all right. So, this gives me a way to relate actually pressure to velocity, this gives me a way to relate pressure to velocity. Now, this has got some relevance. All that I have done so far is try to getting some kind of a relationship of this kind, right. Now, pressure is measurable, right. I can measure the pressure. I have various kind of transducers which can convert pressure into electrical signals, and therefore, I can measure, right. Electrodynamic type, piezo type these days. There are so many of them, pressure transducers are there. But my ear actually it does not depend upon pressure, but it depends upon, I mean, what I hear, how much do I hear in crude sense, or rather in subjective sense, what we call loudness. It depends upon how much energy per unit area is falling onto my ear. That is right. I mean, the energy density. Energy is, so similarly, the intensity that we talked about in case of heat, right. In case of heat, we talked about intensity. So, intensity is nothing but energy per unit area, and how much, the temperature is of course sensible heat, but heat flow per unit area, that dictates how much energy is coming into my body or whatever it is we are looking into, or into the system. Here also energy density is important, and loudness is perceived, right. More energy coming onto per unit area, you will feel the thermal stress more. Similarly, more energy coming per unit area on your ear, you will feel the loudness more. So, it is related to, the loudness is related to energy density. So, acoustic impedance of course will come, and we can relate this, we will see that now. Now, this is a characteristics of the medium. For air it is about 405 rails. So, kg per meter square per second. So, that is how it is defined. Now, intensity of sound is nothing but same thing, energy density, and you remember watt per meter square, power coming in per unit area for heat. Same thing here, it is defined as the average energy passing over unit area, normal to the direction of propagation in unit time, that is power per unit area. So, that the loudness I feel similar as I was just explaining, loudness I feel would depend upon the energy per unit area or energy density. Energy, it will depend upon the energy density, that is right. Now, power per unit time, right, and per unit area. So, power is basically force into velocity. You remember force into velocity, force into distance divided by time, that is your power. Power per unit area is nothing but pressure into velocity, right, pressure into velocity. So, power per unit area is pressure into velocity. Now, my pressure is varying with time. Therefore, when I am dealing with it, I can take instantaneous pressure, but that makes my life more complicated. I am really interested in energy coming per unit area per unit time, energy coming per unit area per unit time. So, what I got to do? I got to integrate it over average energy coming per unit area per unit time. Since it is periodic, it will vary from 0 to t, and ux t velocity, pressure into velocity, that will give me the power, 1 by t will give me what we call intensity. So, intensity is the average energy per unit time per unit area, right, in a medium. in a medium, and that will impinge on my ear as well. So, in a medium, in any medium if I am looking at, it will be this. And remember, U can be written like this, because my acoustic impedance is rho c. Velocity p x t divided by u x t was rho c. So, therefore, I can write u x t in terms of this, and it comes out to be p square by rho c. So, this comes out to be integral 0 to t 1 by t p x t square, right, p x t square, because p square is coming, divided by rho c. Now, this if I integrate this p square over the time period, divide by t, I am squaring it up, then taking its mean, 1 by t means average, and if I take root of that, I call it root mean square, p RMS, p RMS square. So, I am writing it as p RMS square, p RMS square. If I take p average of p, it will be 0, because it's sinusoidal, or course it's sinusoidal, it will be 0, but p square is not 0. So, intensity is related average. When I am dealing with average energy, that will tell me how much is the loudness, that will tell me how much energy is received on my ear, and related to loudness, not exactly not loudness, but related to that, we will see that. So, we can call it p RMS square divided by rho c, p RMS square by rho c, and you can actually find out sin square omega t. If you integrate, sin square, you will convert into cos 2 omega t, etc., and you can find out electrical technology also. You might have done similar sort of thing, because alternating current we do the same thing. So, p RMS square by rho c, p RMS square by rho c. So, intensity of sound is given by p square delta t 1 by t, p RMS square will be written like this, p RMS square, I am saying p square, right, p square x t delta t 1 by t 0 to 2. So, this integral of this, right, and you can, for ideal point source, so you can integrate this and find out what is the factor, but we are not interested. We do not need to look into that, we are not interested really in this. What we understand is that intensity is p RMS square by t, not instantaneous p, at any point, but it is p RMS square by rho c is my intensity at any point. It has its intensity is essentially energy per unit area, per unit time. So, it is scalar quantity, right. So, this is a scalar quantity. So, for ideal source, of course, so therefore, this is how we define p RMS square, and intensity, this is how we define, right. Well, let me see if I have slight other, but I think we have already said it is the average energy passing through unit area in unit time for a medium, average energy passing through unit area through unit time, and in unit time you will have number of cycles. Therefore, you have to find out, because it will depend upon the frequency. So, that is why we are averaging it over the time, and in unit time, that is how it is, right. So, p RMS square, that is how it is coming. Now, supposing I have a point source, just a point source, ideal point source, So, its, let us say its power is W watts, it is emitting W watts in all direction. So, the wave is propagating along all direction equally, right. So, W is the power generated, constant power source, constantly W power, sound power, it is emitting in all direction, sound power, I am talking of sound energy emitting. So, at any distance r from this, how much will be the intensity? Intensity, its power, so energy per unit time. So, per unit area I should do. So, this should be simply I divided by W divided by 4 pi r square. So, simply 4 pi W divided by 4 pi r square. So, simply 4 pi r square, So, intensity for a point source at any distance r from it will be given by W divided by 4 pi r square, right. So, that is it. We will come back to this, but all intensity, some at very small intensity you will not be able to hear at all. As I said, your ear is sensitive to the energy per unit area, per unit time, and that is why we are so much bothered about intensity. So, higher the energy coming in, you perceive. and very high energy comes onto your ear, like a lot of people became deaf during the atomic explosion in 6th August 19 whatever it is 45, or this Hiroshima Nagasaki, permanently deaf, or many died. But even because the sound impact, sound can make you deaf, it is beyond certain level. Or if you stand behind a jet engine directly 120, it's very huge quantity of sound. So you jet blast, I mean you may not be blown away, but your ear will surely go away if you are not along the line close to it. So there is a point beyond which your eardrum get permanently damaged. So all intensities you cannot hear. Similarly, very small intensity you don't hear, like some insect moving onto this, you don't hear, while sometime a dog taking off, still you are able to hear that, or scratches or something. So what I am saying, there is a minimum level below which you can't hear, and there is a minimum level beyond which you can't hear again, I mean because it will be permanently damaged. So there is a lower limit and there is an upper limit as well. This is one issue. The other issue is not all frequencies you can hear. Not all frequencies you can hear. Like I said when I was talking of thermal, infrared heat wave, we also looked at the glass. There is a visual range. So certain portion your eye is sensitive to in the spectrum of electromagnetic waves. So you see certain wavelengths, certain lambda values you can see, visual light range. Similarly, sound also you see certain frequencies only. So the frequencies beyond which you don't hear, we call it the beyond hearing audible range, we call it ultrasound. And you will have similarly infrasound, you remember infrared, ultraviolet. So similarly infrasound and ultrasound. And ultrasound is used for very other mechanical mechanical diagnostics and similar sort of thing, mechanical diagnostics, health diagnostics, both. So we are not interested in that at the moment. So there is an audible range of sound in terms of both frequency and intensity, and this is what is so supposing I plot frequency along this direction, I hear slightly below 20 and up to 20 K. I hear 20 cycles per second to 20,000 cycles per second. So that is audible range of frequencies. This side would be ultrasound, this side will be infrasound, and then there is a bottom line beyond which I will not hear at all, the intensity wise, and there is a high intensity beyond which you will have pain, and still go further you will have permanent damage. So this is called threshold of audibility, this is called threshold of pain, and it is in watt meter square. If you see intensity in watt per meter square, because power per unit area per unit time, average power. So then 10 to the power minus 12 watt is what you can barely hear, and 1 watt per meter square it starts paining, right. So this we call as threshold of audibility, this we call as threshold of pain, and this is the audible range starting from this. So this is the zone which you can actually, this is the zone which you can hear, hearing range is this, right. So typically this is what it is. So this is below threshold sound, this is super sound and so on. So that's how it is. So there is a range that is difficult to handle. So okay, so therefore it means that you see if you look at 10 to the power minus 12 to 1, now it will be difficult to handle in linear scale, 1 to 10 to the power 12 times. So if you take log of this, then this becomes minus 12 to 0, log 1 will be equals to 0, minus 12 to 0. That is also not a very good range, and if I divide by this value, then this divide both of this by this value, this will become, and take log, then this will become 0, dividing 10 to the power minus 12, this becomes 1, this becomes 10 to the power 12, then I vary from 1 to 12, multiplied by 10, then you get 1 to 120. So that is a descent scale, and therefore this was after the name of Alexander Graham Bell. So, we actually express sound levels, as we call it, intensity levels, in a scale called decibel scale, which is a relative scale. Reference is threshold of audibility. So, the intensity divided by threshold of audibility, take log of it, multiplied by 10, take log of it is a bell, multiplied by 10, it is decibel. So, that is why the decibel is. So, there is another reason why we do not handle it in linear scale. Remember, we talked of Weber-Fechner's law, and we said that it is also logarithmically related, your sensation. So, sensation is logarithmically related somehow or other, and therefore, we use it. So, decibel is a relative scale, and you might use it for many cases, not here. Many kind of such signals people use relative scale decibel. So, for example, even in microwave attenuation, you will be talking in terms of decibel. So, decibel is 10 log I by I ref, and we call it sound intensity level. So, intensity levels are expressed in decibels, and quite often we denote by Li. Some people might denote by something else, but here we will keep it Li, right. So, sound, now if it is, you see, intensity is not directly measurable, but we can measure pressure. We can measure pressure, and if I divide it by the reference pressure square, actually, as we shall see, divided by some reference thing, take log and 10 log, that will be a relative scale. So, even pressure level I can express in terms of decibel, pressure level I can express in terms of decibel. So, you can see that LP 10 log P square by P reference square, because intensity is nothing but proportional to P RMS square. Now, whenever now I am talking of P, I only mean P RMS. I am no longer talking of P XT or PA, amplitude. I am not talking of amplitude, I am talking in terms of P RMS. P RMS, because that is what the output you will get from any instrument or anything of that kind, and we are dealing with that situation only. And you remember P RMS square or P reference square. So, P, this would be related to I ref actually, which was 10 to the power minus 12, right. So, this can be, pressure level can be written like this, 10 log P square by P reference square, right. And this reference taken 2 into 10 to the power minus 5, I think. And similarly, for a source its power is W. This is for medium. Somewhere in the air I will measure the intensity. Somewhere in the air I will measure the intensity, and that will fall onto my ear. And this is also because sound pressure level can be measured. Intensity measuring is difficult, because energy measuring per unit area, pressure is easily, sensors can measure them. So, sound pressure level we measure, and the other one is power level. Power level is for source, power level is for source, power level is for the source. So, sound power level is for the source, and that we call as W divided by W ref 10 log. So, power level is for the source, pressure level is for the field, and so is the intensity level. Pressure level is what normally we would be talking about, because that is what is measurable, right. These are related, actually we will see that how they are related, right. So, power level is for source. So, if you talk in terms of a source, you will talk in terms of power level dB. For the field, you will talk in terms of pressure level dB. Unit is same, because they are relative units. So, that is what it is, right. Okay. So, any question if you have, I will take these questions, and then next class we will look into it.